What's up, guys?
So, we should just fail.
Bauhaus Fest. They have comp.
Oh, their comp is this week?
And we don't actually have to do a final exam, we can do a project if you want.
A project that you have only a week to do?
That's how long it's been.
Well, I gotta come up with the project too.
If you like, I could take my biomechanics paper,
Yeah,
and then I control, do search and replace, and
Yeah.
change the word swimming with heat exchange.
if only life were that easy. I wish. All right, it's 1 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing?
Good.
Good to hear. Okay, so we are very quickly winding down the semester. So we have 4 more lectures, including today. So just like I promised, next week, at the very least, next Thursday's lecture, I do want that to be just a review session. And so I'm planning to finish up everything by Tuesday. But we might have some time to do review next Tuesday as well. Okay. All right, so hopefully everyone got my email yesterday with information about the final exam. So I sent that email out and I realized I forgot to put the date and time for the exam on there, but hopefully you guys know, hopefully it's in your guys' calendar already or from the syllabus. So our final exam in this class is going to be 2 weeks from today. So it's going to be Tuesday, May 13th, from 1 to 2:50 p.m. in this room right here, E201. Okay. Now the format for the exam, you were allowed to bring 2 cheat sheets. And so for all the midterms up to this point, you were allowed 1, but since the final exam is going to cover more stuff, you can have 2 cheat sheets. Okay. Same rule as the midterm, so you can have both sides. You can write it or type it, whichever is easier for you. All right. Definitely take a look at the study guide. So if you look at the study guide, you'll see that the final exam is going to cover topics all the way from the first midterm. But it's not going to be absolutely everything. And so, just based on practical difficulties, it's only a 2-hour exam. So it's impossible for me to ask you to learn, or cover absolutely everything on that exam. It's also impossible to study, 15 weeks worth of content, for 1 exam as well. So, so I did cut out some topics. And so make sure you look at the study guide before you start studying. So some of the things I cut out would be things like fins, heat exchangers, free convection, just off the top of my head. There might be some other stuff too, but definitely check out the study guide because I did cut out quite a bit. Okay. Now for the format for the final exam, I'm planning to have 8 short answer questions. That's going to be worth 40% of the points, and 3 problems worth 60% of the points. So obviously, this is longer than the midterm exam, but you do have longer to take the exam for the final. And so that's why the final is going to be a bit longer, especially for the short answer questions. Okay. Okay. Any questions on the final exam? Yeah. Not yet. I think, yeah. Contact me offline and then we'll schedule a time. Yeah, what's up?
Study guide, does it also have short answer questions?
It does, yeah. So the study guide is broken down just like all the midterm study guides. So there's a conceptual section and then a problem solving section. So the conceptual section, that'll tell you everything, cover all the topics that you need for the short answer questions.
Topics that we see on the study guide, it's going to be similar to what we see on the short answer questions.
Exactly, yeah. Or I guess more importantly, whatever is not on the study guide is not going to be on the exam. So.
Okay, thank you.
All right. All right, and I guess good thing for me is that the final exam in this class is fairly early in the week, and so I am planning to have it all graded before the end of the week. So you guys should know, by the end of the week what your grade is. Okay. All right. Any other questions on the final exam or just anything for our last couple of weeks here together? Okay. All right. So we'll go ahead and get started with the lecture today. So lecture today is going to be about radiation exchange. So that's the topic that we started last Thursday. And so we'll get more into it. We're going to do a few more sophisticated examples and then kind of really get into the meat and potatoes of the stuff. But this topic of radiation exchange is the last major topic that I want to go over. There's one more smaller topic I want to do after this, and I kind of forgot about it last week. But that shouldn't take a whole lecture. So that should be probably like half a lecture's worth of content. So I'm hoping to finish all of radiation exchange by this week. Then next Tuesday, we'll cover environmental radiation, which is kind of the absolute last thing. And then we'll start reviewing for the final exam. Okay. Okay, so let's go ahead and pick up where we left off. So let's talk about radiation exchange. Okay. My legs are killing me right now. Over the weekend, we've been having kind of a mold problem in my house, and so I went onto my roof to clean off the mold, but I was scared of falling off the roof, so I was crouching and scrubbing the whole time. So I did my leg workout for the entire year over the weekend. Okay, radiation exchange. All right, so what is that? So we know just from the last couple of weeks that every object that's at a non-zero temperature is going to radiate heat outwards. Okay. And remember what radiation is. So radiation is a very different mode of heat transfer, that we've been talking about so far. Because radiation is the only mode that doesn't require any kind of material medium. It doesn't require any kind of matter or molecules in between the objects, because radiation travels through electromagnetic waves. Okay. So if we have two objects, right? So we'll call this object 1. We'll call this one object 2. Okay. We know that both of these objects are going to radiate heat outwards, okay? And generally, for our purposes, generally we assume that the radiation occurs out in every direction equally. Okay. So, for the first couple of lectures that we covered radiation, we talked about, how do we quantify how much heat comes off an object, okay? But in most practical situations, when you are considering radiation, not only are you interested in the amount of heat that's coming off an object, but specifically how much radiation is going from one object to the next, right? And so what we're interested in is, let's say if we have these two objects, how much radiation is going from one object to the next one here, okay? In other words, what is the radiation exchange between these two objects, right? And so it turns out, this problem is a lot more difficult than it may initially seem, because a lot of it really depends on the geometry of the two objects, okay? Right. Because when you have radiation coming off an object and it's going in all different directions, right? Only a small percentage of that radiation is actually going to go from one object to the next. Okay. Okay. It's not like before where, we weren't, before when we were talking about conduction and convection, we didn't really worry about this all too much because, there's usually a very clear direction for conduction and a very clear direction for convection. And, where where that heat transfer takes place usually wasn't a point of concern. But with the radiation, because it goes out in all directions, we really need to take a look at the geometry of the situation because that affects our result. Okay. Now, normally, if you were to analyze this, from scratch, this would be a very difficult problem to do, right? And so we talk about things like the solid angle and the intensities and things like that. Okay. And so instead, we're going to use something called the view factor. So if you recall from last Thursday, a view factor is a coefficient that tells you the percentage of radiation that comes off one object that hits another. Okay. And so the way that we define the view factor was the following. So we say that, whenever you have a view factor and whenever you have radiation, you always need to take into account what the source of the radiation is and what the target is. And so all of these things like view factors and heat transfers, there's always going to be two coefficients that are associated with it. Okay. So for instance, for the view factor, right, we always define it as, Fij, right, where I here is the source object, and J is the target. Okay. So this is specifically the view factor between object I and object J. Okay. This is equal to Qij, where Qij here, this is the radiation heat transfer between object I and object J. Okay. Divided by AI, EI. Okay. Where this product AI, EI, remember, this is the total amount of radiation emission, total amount of emission coming off of object I. Okay. All right, so we can use these view factors to, more conveniently compute radiation from one object to another, okay? Because the benefit of using these view factors is that, we can often compute them, through other means. And so we don't have to, mathematically derive these view factors for every given situation. Okay. So that was kind of the last example that we did last Thursday before we headed off for the weekend. And so, so the other means in which to compute the view factors, first one is that you want to use is if there's any view factors that you can determine based on inspection, you can do that. And so if there's anything about the geometry that's, fairly obvious, you can just determine the view factor from there. And so there will be certain situations where you can determine this view factor is going to be 0 because it's impossible for this surface to radiate on another surface. Or maybe this view factor is 1 because, this surface can only radiate onto this other surface. And so, you can come up with some by inspection, usually pretty easily in some cases. All right, so another way that we can find view factors is we can use what's called the reciprocal property. And so the reciprocal property, basically what that means is that two view factors that of two objects are related to each other through an equation, right? And so for instance, if we know Fij, right? So the view factor from object I to object J, if we multiply that by the area of object I, okay, the reciprocal property basically says this is equal to Fji, right? So the view factor going from the other way, from object J to object I, multiplied by the area of object J, okay? Okay, so that's always true. And so typically, once you find the view factor from one object to the other, you can use the reciprocal property to find the view factor going in the other direction. And oftentimes they're going to be different. And so, just be careful with that. Right? Okay, so another way that we can determine view factors is to make use of something called the summation property. And so basically, when you have an enclosed surface, all of the view factors coming from one object, so all the view factors involving one object as a source, all of those should sum up to one. Okay, so this is only for enclosures. Okay, basically the summation of Fij, where J goes from 1 to N. Okay. All that has to equal 1, because when you have an enclosed space, when an object emits radiation, it has to hit something else. And so, if you add up all those percentages, they should equal 1. Okay. Okay, and then the last resort, if you're not able to determine a view factor from the 3 above here, the last resort that you can refer to is, usually for a lot of common situations, view factors are tabulated in these tables. Okay. So last resort, if you can't find a view factor, then, maybe that geometry is given in a table somewhere. And so you would look that up in the table. And so actually the example that we're going to do today is going to make use of that property there. Okay. Okay. So a little bit of a lengthy review, but a lot of today is just doing examples and kind of building on this. So I wanted to make sure I kind of do a thorough review of this stuff. Okay. Any questions on any of this? Okay. All right. So let's jump into another example. Okay. So let's consider a rectangular furnace. Okay. Okay. So not necessarily a space application, but this is a situation with very high temperatures. And so this is likely a case where radiation is going to be significant. Okay. Okay, so in our rectangular furnace, we have 3 walls. Okay, so we have something that looks like this. We're going to call the one on the right here surface 1. Okay. And surface 1 is going to be at a temperature T1. T1 is going to be 1000 Kelvin. So extremely, extremely hot. Okay. All right, down here, we're going to have surface 2. And so surface 2, we'll say T2 here is at 800 Kelvin. Okay. And on the left-hand side here, we're going to have surface 3. And surface 3 here is going to be 600 Kelvin. Okay. All right, we also know a bit about the geometry here. So this length here. So the length of surface one, the one that we see in the drawing here, this is 0.5 meters. Okay. And the length of surface two here, we'll say this is 0.1 meters. Okay. So the drawing isn't quite to scale, but and so this this furnace is quite narrow. Okay. Okay. And another thing that we're going to assume, just so that we can kind of compute areas here, is that the length going into the page, or the width for all surfaces, is going to be 1 meter. Okay. Okay, so I circled that there just so that you kind of see. So all three of these surfaces here, when you look at kind of its width into the page, they're all 1 meter. Okay. Okay. Oh, one other thing. So this furnace here is open to the environment. And so the environment here is going to be at an ambient temperature. Okay. So outside furnace. Okay. And, for here, it's only going to be relevant in that gap. So in that gap between surface one and surface three, right? Okay. So in that gap, we have just simple ambient temperature here. So T infinity is equal to 300 Kelvin. Okay. So that's about room temperature. Okay. All right, so that's the geometry here. So actually, let me draw in the ambient temperatures just so you can see. So ambient temperature will be, we're effectively going to create another surface here. And so we can say that we have a surface 4, where surface 4 here is going to be at T infinity is equal to 300 Kelvin. Okay. Okay, so even though technically it's not an enclosure, this geometry is open. What you're going to see is that we're going to draw kind of like a pseudo surface, just so that we can apply our properties. And so if we kind of draw an imaginary surface, surface 4, and we say that that surface is the same temperature as the environment, then we have an enclosure here. Okay. Okay. So with all of this in mind, let's state the problem here. Okay, so we want to compute 3 things here. So first thing we want to compute is we want to compute the radiation exchange between surface 1 and surface 2. Okay. Number 2 thing we want to compute is we want to compute the radiation exchange between surface 1 and surface 3. Okay. And last thing we want to compute here is we want to compute the radiation exchange between surface 1 and the outside, and the surroundings. Okay. So that's going to be our pseudo surface 4. So even though, there's technically not a surface there, surface 4 is kind of what leads to outside the furnace. We want to find out how much of radiation from surface 1 is basically leaking out to the outside. Okay. Okay. All right. So this right here is a pretty typical radiation exchange problem. And so this problem here actually is quite similar to your homework as well. So this is a good one for us to do together. Okay. Any questions on just the setup for the problem? Okay. All right. So let's go ahead and get started. Okay. So let's start with part 1 here. So part 1, we want to find the radiation exchange between surface 1 and surface 2, right? So in other words, what we want to find is Q12. Okay. or I should say, Q12 here, this is the, I apologize. So Q12, this is the radiation heat transfer from surface 1 to surface 2. Okay. But what we want in this problem is actually radiation exchange. So not only do we need Q12, we also need Q21 as well, because that's the radiation going from surface 2 to surface 1. Okay. And so the radiation exchange is actually going to be the difference between these two. Okay. Now, which one is going to be higher here, right? And so, there's going to be a way for us to order this in a way that, is going to give us a positive number, right? And so in this case, because surface 1, we know surface 1 here is at the highest temperature, right? So T1 is 1,000 Kelvin. There's nothing else that gets higher than that, okay? And so what we expect here is that because surface 1 is at a higher temperature than surface 2, there should be a net amount of heat transfer that goes from surface 1 to surface 2, right? Now, there's going to be some heat transfer that goes from 2 to 1, right? But it's not going to be as high as the amount going from 1 to 2, okay? Okay, so in this situation, the radiation heat exchange is going to be Q12 minus Q21, okay? Yeah.
Ever possible that you might ask instead for the radiation exchange from surface 1 to 2? Or
Yeah.
it's always between the two?
Yeah, so there you have to kind of read the problem too. So sometimes I might ask you, what is the radiation heat transfer from one surface to the other one? Okay. And so in those cases, in that case, you would just compute this. And so for instance, if I just ask you what's the radiation from surface 1 to surface 2, I would just want Q12. But when I'm specifically asking for the radiation exchange, that one, and you need to actually compute the difference. So you not only need Q12, but you need Q21 as well. Okay.
Thank you.
Yeah, so it can be a little bit tricky with the wording. So just kind of make sure you kind of read the problems carefully. Okay. All right, so let's quantify each of these two. Let's quantify Q12 and Q21 in terms of their view factors. Okay. So Q12, this is going to be equal to F12, right? Right, so F12 is the view factor from surface 1 to surface 2. This is multiplied by A1 times E1. Okay. Okay. Where we know what E1 is going to be, E1 here is just the emission from surface 1 here. Okay. Okay. So if we plug in for E1 here, this is F12 times E1 times sigma. Remember, sigma is the Boltzmann constant, multiplied by T1 to the 4th power. Okay. Okay, and then Q21, this is going to be equal to F21 multiplied by A2 E2. Okay. All right, and so if we plug in for E2 here, this is going to be F21 times A2 times sigma times T2 to the 4th power. Okay. Okay. So everything, we have a lot of the variables in here already, because if we look at the problem, right, we know the areas for both of these surfaces, right? Because we know their geometric dimensions, we know their length, and we know their width going into the page, right? The Boltzmann constant is also known. So sigma, that's always just going to be a constant value. So remember, that's 5.67 times 10 to the minus 8. Okay. And we know their temperatures, right? So the temperatures were also given to us in the problem. So we know T1 and we know T2. In fact, we also know them in terms of Kelvin as well. Okay. Now, the one piece of information that we don't have, which is typically going to be the case in these radiation exchange problems, is going to be the view factors. And so, kind of the name of the game, or kind of what you end up doing in these radiation problems is, how do we solve for the view factors in these types of situations? Okay. So let's see if we can determine the view factors from this, from this geometry here. Okay. So first thing we should notice is that, we can use our reciprocal relation because these are view factors for reciprocal surfaces, right? And so first thing we can say is that from the reciprocal property, okay, we know that F12 multiplied by A1 is equal to F21 multiplied by A2. Okay. Right. And so what this tells us is that if we're able to find one of the view factors, so let's say we were able to find F12, then we can find F21 as well. Okay. So that's good. So that means, we're not searching for two now, we're searching for one of our view factors. Okay. Okay, good. So we're going to make use of the reciprocal property. Okay. But that still leaves us with the problem of finding one of these to begin with. So either F12 or F21. So we need to find those in some way. Okay, so let me kind of scroll back up here. Right. And let's look at our 4 different methods here to solve for the view factors. Okay. So we've already used the reciprocal property. Okay. Right. But let's see if we can find the other view factor from either inspection or summation. Okay. Okay, let's try inspection first. And so, we want to find the heat transfer or the view factor between surface 1 and surface 2 here, right? And so surface 1 being this one here, and surface 2 being this one here. Okay. Now, based on inspection here, we can't really, there's not much that we can really say, just because we know that surface 1 here is going to radiate to all 3 of these surfaces here. So surface 2, surface 3, and surface 4. Okay. And so in this case, there's not much that we can do with inspection. I guess the only thing that we can really say is that the self view factors in all 4 of these surfaces case are going to be 0 because they're all perfectly flat. And so, one thing we can say is that, F11, F22, F33, F44, all of those are going to be equal to 0 because these are flat surfaces. But beyond that, there's really not much we can determine here from inspection. Okay. So inspection has been ruled out. So there's nothing immediately obvious from our geometry here where, we can inspect and say that's the view factor. Okay. Besides the fact these are all flat surfaces. Okay. Okay. All right. So that's the only thing that we can get from inspection, but nothing too useful there. Okay. Let's check the summation property. Okay. Now the summation property says that, when we have an enclosure, the sum of all the view factors involving that one surface are going to sum up to 1. Okay. Let's see if we can apply that here to solve for the view factor. So, you know, let's consider just all the view factors coming from surface one here. Right? Okay. So let's test that out. So let's test the summation property. And so let's look at surface one. Okay. Because remember, for the summation property, you have to choose a source. And so the summation property says all the view factors from the same source have to sum. Okay. Okay, so from the summation property, we know that F11 plus F12 plus F13 plus F14. Okay. I'm calling that pseudo surface surface 4, right? All of these have to equal 1. Okay. Or when you sum them up, they has to equal. Okay. All right, so the only one that we know from this expression is F11. So F11 we know is 0 just from our inspection. Right? So whenever we have a perfectly flat surface, then, you know, the self view factor is 0. But for the other ones, you know, we don't really have any information on those, right? And so, you know, we can plug in, right? So we can plug in for F12 here, right? So we can say F12 is equal to F21 times A2 over A1, but that doesn't really help us out at all because F21 is still unknown, right? Oops. And so in this particular case, you know, our summation property doesn't really help us because F12, F13, and F14 are all unknown. Okay. This might help us out for a later part of the problem, but for now, you know, we're going to say this is just not helpful for us. Okay. Okay. And so if we go back up to our list of different methods to find the view factor, right? So we can cross off summation for now, okay? Because summation didn't really help us with anything here, okay? So that leaves us with just our last resort here, which is a table expression, okay? And so in this situation, you would have to look up for an expression in a table. Okay? And specifically, the tables that have this information in the textbook is table 13.1 and 13.2. Okay. And we'll see that if there's anything there that can help us kind of break this stalemate here and get us something that we can use to compute the view factors. Okay. But before we do that, are there just any questions on how we, or just any of the logic or any of the you know, how we got to this point here? Okay, good. Okay, so let's look in the table. And in this particular case, it's going to be 13.1. Okay. Turns out in table 13.1, there is a situation here that can help us. So in table 13.1, you'll see that there is a scenario for perpendicular plates with a common edge. And so if you look at that table in the book, and so let's say we have, you know, one surface like this, well, this is called surface 1, and we have another surface right next to it. Okay. So you can see that these two plates are perpendicular to each other. So the angle between these two plates is 90 degrees, okay? And they share a common edge. And so you can see here that right here, they share that edge in between those two surfaces. Okay. Okay. And so in this situation, there is a formula for the view factor. Okay, so for this situation, we have F 1, 2. And the other thing that you need to know is you need to know the length of these surfaces. And so if the length of surface 1 is L1, and the length of surface 2 is L2, then the view factor between these is 1 plus L2 divided by L1 minus 1 plus L2 over L1 quantity raised to the 1/2 power, all divided by 2. Okay. Okay. So in this situation, we have everything that we need for this equation here, right? So if you go back up to the figure, right? Right. We look at surface 1 and surface 2. We know their lengths. They are perpendicular surfaces and they do share a common edge. And so this would be something that we can, we can use to compute it. Okay. Okay. So if we plug it in, and so in particular, if we have L1 is equal to 0.5 meters, L2 is equal to 0.1 meters from this problem. Okay. What we get is F12 is equal to 0.09. Okay, so that breaks our stalemate here. So that basically gives us a way to kind of solve this problem, because now that we have F12, right, we can compute F21 from the reciprocal property. Because we have F21 here is equal to F12 multiplied by A1 over A2, okay? And so if we plug in the numbers for this one, we have F12 is equal to 0.09, okay? Both surface 1 and surface 2 have the same width into the page. And so I'm just going to multiply this by the ratio of L1 over L2, right? Or L1 here is 0.5 and L2 here is 0.1, okay? So technically for this one, you have to use the surface area for the object, but in this case, they both have the same width into the page. And so that's why I changed A1 over A2 to L1 over L2, okay? Okay, and so we have that ratio L1 over L2 is going to be just 5. And so that means F21 is going to be equal to 5 times 0.09, which is 0.45. All right, and so finally, now that we have these two view factors, we can compute the radiation exchange between surface 1 and surface 2. Okay, we have Q exchange is equal to, let's see. So this is equal to Q12 minus Q21, okay, which is equal to F12 times A1 sigma T1 to the 4th minus F21 A2 sigma T2 to the 4th, okay? All right, we have absolutely everything here. So we have both the view factors. We just computed them, right? The areas we can compute. So areas are just going to be the length of the plate multiplied by the width, okay? Sigma is the same, and so I don't think we've written down sigma for today. So let me actually write it down. Okay? So sigma, remember, is 5.67 times 10 to the minus 8 watts per meter square times Kelvin to the 4th. Okay. So remember, this is the Boltzmann constant. And of course, we know the temperatures as well. And remember, when you plug in temperatures for radiation, you have to plug it in Kelvin. Okay. Okay, so we plug everything in here, right? What we get is the radiation exchange between surface 1 and surface 2 is 1506 watts. All right. All right, any questions on how we got that result there? Yes, question.
When determining the view factor, we have to resort to the tables. How would that work on the exam?
You don't need to put the tables on your cheat sheet. I would just give you the expression that you need. Either that, or I would give you the problem in a way where you don't need the table for that. So, maybe I would give you this problem, and I would just say straight up. So from this problem here, it's, I would just give into you, let's say F12 is equal to 0.09, and then you would be expected to go from there to compute the other view factors. Yes, that one's probably more likely for this problem. Yes. All right, any other questions on how we got this result here? Okay, all right, so let's do the second part of the problem. So second part of the problem asks us to find the radiation exchange between surface 1 and surface 3. Okay. 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 So in this situation, we're going to need Q13. Okay. Where Q13 here is F13 times A1 sigma T1 to the 4th. Okay. And Q31, which is going to be F31 A3 sigma T3 to the 4th. Okay. All right, so we have the same issue here. And so, in order for us to compute this radiation exchange, kind of the bottleneck for our process here is computing the view factor between surface 1 and surface 3. Okay, because we're given everything else in the problem. And so, we can compute everything else. Okay. Okay, so you can take the same approach that we did for the first part of this problem. And so, the geometry for this one is a little bit different. And so if you look at surface 1 and surface 3, right, it looks something like this. Okay. And so instead of having the two plates perpendicular to each other, now we have two plates that are parallel to each other, separated by a certain distance. Okay. So these are parallel plates. Okay. Separated by a certain distance. Okay. Okay. So, after doing the first part of this problem, and you had to look up table 13.1 anyway, probably what you're going to notice is that in 13.1, in table 13.1, this situation is in that table as well. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . Okay. All right, and so I will give you the expression for that here. Okay. Okay, so F13 from that table is going to be given by we have W1 plus W3 quantity squared plus 4. Okay. All of that raised by a square root, okay, minus W3 minus W1 quantity squared plus 4. All of that square root as well. All that divided by 2 times W1. Okay. Now, what is W1 and W3 here, right? So W1, W3 here is not the actual lengths. Okay. Right, so the actual lengths of the plates here are L1, L3, but what actually matters in this case is also going to be the separation between these two plates, okay? And so if we call the separation between the two plates D, okay, then W1 here is the ratio L1 divided by D, and W3 is the ratio of L3 divided by D, okay? So not only do the lengths of the plates themselves matter, but how far they're separated also plays a big role in this equation as well. Okay. Okay. So we have everything we need in the geometry to compute this view factor. And so if you plug everything in, what you get is F13 is equal to 0.82. Okay. Okay. So this tells us that, the majority of the radiation that comes off from surface 1 and surface 3 is going to hit the other parallel surface, which makes sense because these plates are very, very close to each other. Okay. Okay, so that's one way to do it. And so, if you have the table open and it's there and you see it, you can do this. Okay. But I would actually make the argument that you could actually solve for this view factor without looking up in the table. Because what do we have? So, if we go back to our geometry here, right? Right. Already in this problem, we've already solved for F12, right? So F12, we know this from part 1. Okay. Or, we've already computed it, right? Let's see if we can use this information to compute F13 without using the table. So let's see if we can use the summation rule to compute F13. Okay. So what is our summation rule? So our summation rule says that F11 plus F12 plus F13 plus F14 has to equal to 1, right? Because if we create that kind of phantom surface, the pseudo surface 4, right, we basically created an enclosure. And so that means that if we sum up all the view factors from all 4 of the surfaces, they should equal 1. Okay. Okay. But at this point in the problem, we can actually start to fill in some of these quantities here, right? Because we know that F11 is equal to 0, right? Because it's a flat surface, it's impossible for surface 1 to radiate on itself, okay? We know F12. We know F12 is 0.09 from part 1 of the problem. Okay. So F13, I know the answer is right above here because we found that from the table, but let's pretend that we don't know F13 yet. Okay. Now, that just leaves the only one here, F14, okay? But I would make the argument that we already know F14 based on the symmetry of this problem, okay? Now, if we go back up to the problem statement here, right? It's a little bit of a messy situation. But if you look at it just purely from its geometry, I know surface 4 is at a very different temperature than surface 2, right? But looking at it just from the geometry, surface 4 with relation to surface 1 is exactly the same as surface 2, right? Right? Because if you're standing on surface 1 and you're looking at the other 3 surfaces from surface 1, right? Surface 2 and surface 4 are the exact same length, right? It's just one of them's on our left and the other one's on our right, okay? And so in this case, we can say based on inspection and based on what we already know from F12, we can say that F14 here should be equal to F12. Okay. Just because of the symmetry and what we notice from the geometry in the situation. Okay. Okay, so let's take that information and let's apply that to our summation rule at the bottom here. Okay. So if we know that F14 is equal to F12, then we know that this is 0.09. Okay. So from inspection and symmetry with surface 2. Okay. Right, so let's plug all of those quantities in, and you'll see that we're only left with one quantity here, which is F13. Okay. All right, so F11 is 0. I'm just going to ignore that one. F12 is 0.09. Okay. F13 is our unknown here, so I'll leave that as unknown. F14 we just determined is 0.09 as well, just based on inspection. Okay. And then based on the summation rule, if we add up all of these view factors together, it should equal 1. Okay. And so if we do our simple arithmetic here, we get F13 is equal to 0.82, okay, which is the exact same result that we got from looking up the expression in a table. Okay. Right. So both methods are valid here. And so if you prefer to just look up the expression in a table, you're good at kind of looking at that geometry and plugging in, by all means, that's going to be great. But sometimes, sometimes if you can avoid going to the table, sometimes you can kind of make clever use of the reciprocal property or the summation property, or just, symmetry in the problem, to find the view factors like this, right? And this is perfectly valid as well. So, you kind of have your choice in terms of how you want to kind of tackle these problems. Okay. All right. Any questions on how we got this view factor F13? Okay. All right. And so now that we have F13, we also have F31 as well. And so if we plug all of that in, right? We plug all that in here. And so if we say that we're computing Q exchange, which is going to be Q13 minus Q31. Okay. So we basically plug in everything that we had up there. What we get from this exchange here is, let's see, 20,234.2 watts. Okay. Okay. Good. So again, the name of the game here and kind of the task that you're going to have for radiation exchange problems, really most of it kind of boils down to just computing the view factors between all the different surfaces in the problem. Once you have the view factors, you have basically everything that you need for the problem. Okay. All right, any questions on this example before we move on? Yes.
The temperatures, does it matter if you plug in as Kelvin or Celsius?
It does. And so you want to make sure that you plug in as Kelvin for radiation. Yeah, because you're raising it to the fourth power. Yeah. Mhm. Okay. All right, so I know there's one more part of this problem, and so that was the radiation exchange between surface one and the environment. But that part is pretty straightforward here because now that we have F12, we know that that's equal to F14. It's mostly just plug and chug from there. So I'm going to skip that one. That is worked out in the notes. And so if you wanted just to check your answer, but I did want to spend the last 15 minutes today kind of introducing the next topic, just so that we kind of jump right into more examples next time. Okay. Okay, so for the last 15 minutes today, we are going to start introducing what I call gray body radiation exchange. Oops. Yeah.
So is this stuff, that's passed on work gonna be on the exam?
So this stuff is on homework 7.
Okay.
So it will be on the exam. In fact, you can expect a problem like this on the exam.
Thank you.
Mhm. Okay. All right. Gray body radiation exchange. So far, we've done kind of 2 examples. We did kind of one short example last Thursday, and today we kind of did a more in-depth example. So far, we've kind of assumed ideal conditions for radiation. Okay. And those ideal conditions refer to the emissivity of the surfaces involved. Okay. And so in other words, we've basically assumed that we've had black body radiation this whole time. Okay. Right. And so if you recall from last week, black body radiation, all that really means is that all of our surfaces here are perfect emitters and perfect absorption. Okay. Okay. So our emissivity epsilon has been assumed to be 1, and our absorptivity also has assumed to be 1. Okay. Okay, but that's not the case, for the vast majority of practical situations. Okay. Okay. So when you talk about real surfaces, we're not going to have perfect emission or perfect absorption. Okay. There's going to be situations where our surface is not going to emit as much heat, just because the surface properties are not that, perfect. But also, more importantly, even when you consider all the radiation that hits a surface, some of that radiation may be reflected, and some of the radiation may be transmitted through the object as well. Okay. And so that's kind of what we're going to focus on for this kind of section here. Okay. Okay. So among these, reflection is actually the most interesting one, because when radiation gets reflected from an object, you know, practically speaking, reflection is kind of the same thing as emission, because emission is the amount of radiation coming off an object. But if radiation is reflected, you know, that's also going to be coming off the object and going to something else as well. Okay. So oftentimes, you know, when we're doing calculations involving kind of real surfaces, oftentimes we kind of lump together emission and reflection together, because both of those, you know, both of those describe some radiation that's coming off of an object. Okay. Okay. Okay, so the way that we combine these two is we kind of define a new quantity. And so I know, you know, radiation, I'm kind of just throwing all these different terms at you just because, you know, really we're kind of speed running through radiation. So, you know, normally, you know, for kind of a more sane case, we'd spread out a lot of these concepts over weeks, but, you know, we're kind of just trying to cram all of it in together. So unfortunately, this is another term. Okay. So this term is called radiosity. Okay. So radiosity here is the combined effect of emission and reflection from an object. Okay. So it's interesting. Radiosity, actually, we give it the symbol J. Okay. So J here is equal to E, where E here, that's our emission. So that's kind of what we've been working with up to this point. Okay. Plus rho multiplied by G. Remember, rho here, this is our reflectivity. Right? So reflectivity is the percentage of radiation that hits an object that gets reflected off. And G here, this is our irradiation. Okay. Or in other words, all of the radiation that hits an object, right? So the reflectivity is the percentage of the irradiation that comes off. So the radiosity is simply just the sum of these two things. Okay. Okay. Good. And so we're gonna start to consider these now, because now we're gonna look at surfaces where, you know, the emissivity is gonna be less than 1. Okay. So remember, this tells us that our object is not a perfect emitter. Okay. And also the absorptivity is going to be less than 1. Okay. So remember, that tells us our surface is not a perfect absorber as well. Okay. And we're going to consider reflectivity greater than 0. And so, you know, some radiation is going to be reflected. Okay. All right, so we won't get into the formal calculations till Thursday, but I do want to kind of show you a bit of our approach. And what you're going to see is that we're going to get some help from an old friend. Okay. Okay. So what do I mean by that? So let's kind of bring things back a bit. Okay. So, you know, this, you know, I'll bring it back to radiation in a second, but this kind of is a throwback to kind of our very first unit here. Okay. So let's look at conduction through a wall. Okay. Okay, so let's say that this wall has a certain thickness, so we'll call it L. It's made of a certain thermal conductivity K. Okay. And let's say that we know the cross-sectional areas. Oh, question, yes. Oh, sure. Okay. And let's say that we know the cross-sectional area for that convection or conduction as well, excuse me. So let's say that we know kind of the area here, and we know its area. Okay. And we'll say the left side is at T1, right side is at T2. Okay. So how did we quantify the heat transfer from T1 to T2, right? And so what we say is that Q is equal to T1 minus T2 divided by the thermal resistance in the wall. So this is L divided by K times E, right? Or in other words, if we had a thermal circuit here, right? Okay. Right? Our thermal circuit here, we have T1, T2, and our resistance in between. Questions? K times A. Mm-hmm. Okay, let's look at a similar situation with radiation, especially with the example that we just did. Okay. Okay. So with radiation, right? So let's say we have our two surfaces here. So surface 1 is at T1, surface 2 is at T2. Okay. Let's write out the expression for radiation exchange. Okay. Okay, so if we look at radiation exchange between these two surfaces, we just did an example like this. So this would be Q12 minus Q21. Okay. So Q12 here, that's F12 times A1 sigma T1 to the fourth. Okay. Right, so we're making use of our view factors here. And then Q21 be F21 A2 sigma T2 to the fourth. Okay. Okay. I'm going to simplify this expression a little bit. Basically, exactly what we did in the previous example, except I'm going to be a little bit more explicit here. Okay. So from the reciprocal property, we know that this product of F21 and A2 is equal to F12 A1. Okay. And so if we write out our expression for heat transfer, we get F12 A1 sigma, right? So now both expressions here have that term there with it. Okay. And then if we multiply this by T1 to the fourth minus T2 to the fourth. Okay. Okay. And this right here is Q exchange. Right. Right. So after applying our reciprocal property, then we can make this simplification here. We basically did that in the last example. Okay. I'm going to put this in another form just so that it's a little bit more familiar. Okay. What if I did this? And so what if I did sigma T1 to the fourth minus T2 to the fourth divided by 1 divided by F12 A1. Okay. So it's the same thing. It's just that, I put the F12 A1 in the denominator. Okay. And so the reason I did that is that hopefully you see that these two expressions are of similar form, right? So what if we take this idea and what if we can make something called a radiation thermal circuit? Okay. Where we have a circuit that looks like this. Okay. Where on one hand, we have sigma T1 to the fourth. On the other node, we have sigma T2 to the fourth. And the resistance in between them consists of the view factor. 1 over F12A1, or 1 over F21A2, right, depending on which one that you have. So I think, this is a very fitting way to kind of end the semester. So we started this whole semester talking about thermal circuits. We're going to end the semester talking about thermal circuits. So you can dread it, you can run from it, but thermal circuits arrives all the same in heat transfer. Okay. All right. Any final questions before we wrap it up for today? Yes.
Is it only for assuming gray bodies or for black bodies?
So far, this is we've assumed for black bodies. And so what we're going to see on Thursday, we're going to modify the circuit for gray bodies. And so what that's going to do is it's going to add some additional resistances in our circuit for us. Yeah, good question. Okay, all right, so that's all we got time for today. And so hope you guys have a good rest of the day. Thanks for coming, and I will see you all on Thursday. It depends on which one's higher. So in this case, we did 1, 2, minus 1, because T1 is higher than 2. But if T2 is higher than T1, then you just swap it, because typically you want T to be
Yeah.
Question for, we're doing like this. I don't understand how like we relate.
Yes, it's open, but if you draw kind of an imaginary line here, the geometry is kind of the same. It's a box. And so even though it's open here, we can say that, everything that passes through here, it's as if it's pretend that it's the surface, it's not the same as
So we can do that like whenever there's like.
Exactly. Yeah, and that's what you're gonna do most times. Pretend there's a surface there, just so that you can apply the summation. Andrew? Yeah.
You can scroll back up on the slide to, when we did our zoom factor for 1, 3.
Yes.
But
Yeah.
second, let's see if I can bring up my exam.
Oh, yes, in my office. Yeah, we'll just come by after.
Also, I scheduled that.
I saw. Yeah, okay, yeah. Which is Thursday. Yeah.
Can I come in the office on the day to do like an exam review?
Yes.
You said you're doing it Thursday.
Yeah, I should have some time, so I'm gonna finish this up I'll probably finish up the rest of this on Thursday. And then Tuesday, I have just maybe like a 20-minute lecture on radiation, to the environment. And then there's gonna be some review that day, but absolutely Tuesday on Thursday, you can come in for a review. Yep.